Okay, thank you very much for the introduction. So I'd like to begin by thanking all the organizers, both for the opportunity to speak today, which I appreciate very much, but also for having organized this seminar for the past year. I think for many of us, the pandemic has been sort of very isolating in many ways. And for me, it's been really nice to have something that brings us together and lets us hear each other talk for a bit. So I appreciate that very much, and I'd like to thank the organizers for that. So today I'd like to try to contribute as best I can. And as Katya mentioned, I'll be talking about optical inverse problems with local data. So let me try to give you an outline of my talk. So I have four principal problems that I want to talk about today, which I've sort of listed here. But this is actually a little bit misleading. So principally, I want to talk about this one in particular, a transport model for optical tomography with local data. Because this is a problem that I've written about a little bit recently. But I also want to talk about the context of this problem, which I think is also very interesting. And it involves these other three problems that I've listed here. So I'm going to talk a little bit about all four, even though I'll concentrate mainly on this one. But before I do all of that, I'm going to start with an introduction to explain what all of this is about. And I think, as usual, if anybody has questions, please feel free to ask. I think it's nice to, on these calls, to get a little bit of discussion going and not just be talking into a screen, although I'm happy to do that as well. All right, so let me start with an introduction, and I'll start by talking about what I mean by optical tomography. So optical tomography is the process of reconstructing the internal optical properties of an object by making measurements at the boundary. And what does that mean in plain language? So basically, the idea is that you have a source of light that's shining through an object of interest. And when I say making measurements at the boundary in plain language, I really just mean looking at the light that comes out of the object. So here's a picture. This is just a picture of an ordinary flashlight that I've covered with my hand in a dark room. And you can see that there's light coming through my hand, and you can try to think about reconstructing the internal properties of my hand for measurements of light at the boundary. So this is what I mean by optical tomography. And there's lots of applications of this idea because, as you can see in the picture, right, most biological tissues transmit light to some extent, including a lot of tissues that you might not normally think of as transmitting light. Right, so you might probably normally think of hands as opaque objects, as objects that don't transmit light. But if you have the right setting and not even a particularly bright light, I mean, this is an ordinary flashlight that I have in the picture. If you use the flashlight on your phone, you can typically get this effect in a dark room. With not a particularly bright light, you can see that a fair bit of light is transmitted not only through the cracks between my fingers, but also just through the tissue of my hand. Right, so there's a lot of applications for this in terms of imaging biological tissues. But you can also sort of see the problems and the limitations in this photograph too, right? Because I will promise you that my hand contains bones and blood vessels and other structures of interest, but you can't see any of that in the picture. And the reason is that the light in my hand is scattering. So scattering means a lot of things in different mathematical contexts. But here what I mean by scattering is just that the light particles inside my hand are bouncing around a lot off the cells and whatnot inside my hand. And so if you look at the light on the boundary of the hand, you're not just seeing, right? So if you look at the light right here where my cursor is, you're not just seeing the light that's come through that one point in my hand. You're seeing the light that's come through just a sort of a smeared out region around here that's bounced around a lot in a smeared out region around here. And so you see a smeared out version of the inside of my hand. And you can see a little bit of structure here and there, but for the most part, you can't see what's inside my hand. And so this problem of scattering is the thing that turns optical tomography into a mathematical problem. Right? So you have to figure out how to overcome scattering with some sort of mathematical work. So in order to do that, you need a mathematical model for light propagation in a scattering medium. And there's lots of possibilities for the mathematical model we can consider. But today I want to consider two of these. So the transport models and the diffusion models. So I'll explain a little bit more about what these two models are. But I also want to take the time to mention that there's two main classes of optical inverse problems I could talk about: tomography problems and source problems. So roughly speaking, by a tomography problem, what I mean is that the sources of light are known, or they're controlled by us as experimenters. So we can set the sources of light as we see fit. And the unknown things are the optical properties inside the medium. Right? So what are the coefficients of the optical equations inside your medium? That's a tomography problem. But you can also think about source problems, right, where the source of light is unknown. So the optical properties are known, but it's the source that you'd like to reconstruct. So if you think back to the picture of the hand, right, the tomography problem is saying that I can control the flashlight and I want to find out what's inside my hand. The source problem is saying that I know what my hand looks like and I'm trying to figure out what the source of light is. And so between these two classes of problems and these two models for light propagation, I end up with 4 problems, and those are the 4 problems from my introduction. So let me talk a little bit more about what I mean by these 4 problems. So I want to begin by explaining what these 2 models for light propagation are. So the transport model and the diffusion model. And I want to begin with the transport model. So I'm going to consider a domain in R3. And 3 just because you know, I want to fix a number of dimensions, and we happen to live in 3 dimensions as far as we know. And I want to consider a function that takes as argument a point in the domain and a direction in the unit sphere, and spits out a number, right? And so the way I want to think about this function, which I call the specific intensity of light, is that u of x theta describes the intensity at the point x in the direction theta. So you imagine standing at a point x in the domain and looking at the light that's coming to you in direction theta, and that's the intensity of light you see is what u of x theta describes. So it takes both a point and a direction, and it gives you an intensity. And then if you want a model to talk about how u of x theta behaves, so you can look at the directional derivative of u of x theta in direction theta. So you fix a theta, you think about the light that's traveling in direction theta, and you look at its directional derivative in direction theta. So you look at theta dot the gradient in the x variables of u of x theta. And then in a scattering medium, what happens is that you lose something that's proportional to the amount u of x theta. And the reason you lose something is because you have light that scatters out of your original direction. So some of the light that arrives at x in direction theta will bounce off something at x and travel out in a different direction. And so that will be light lost to u of x theta for that fixed theta. And then you'll also gain something, because if you think about the light that arrives at x in all of the other directions theta prime, some of that light will be integrated up and then spit out in direction theta, right? Some of the light that arrives at x from other directions will bounce off and be added into your direction theta. Okay. So if you look at the directional derivative of u, you lose something and you gain something due to scattering. And the 2 terms look like a little bit like this. So I want to mention that you can make this model a lot more complicated, right? So I've chosen the coefficients of the outscattering and the inscattering to basically cancel out. So there's no absorption or gain in this process. But I mean, this is a little bit unphysical if you like. Typically, there's at least a little bit of absorption. So you can also like think about more complicated models with some absorption factor as well. And you can also think about more complicated scattering kernels, right? So I've said all of the light that arrives at x is integrated up equally with no weight here in the integral, and then spit out in direction theta. But you can also imagine some more complicated scattering kernels in here, so it's weighted in some way. And so these are all great things to think about, but for the purpose of this talk, I want to consider this simple model here. Okay. Oh yeah, and I have not necessarily been too precise in terms of regularity that I'm talking about in all of these slides. But I want to say that for the purpose of this talk, everything is as regular as we need it to be. So in particular, sigma here always represents a uniformly positive smooth function. So we don't need to worry about any anomalies as sigma has singularities or sigma goes to 0 or anything like this. There's always some scattering. So let's see. So for the purposes of easy writing, I'm going to, for the most part, drop the arguments in here. And I'm going to represent this average integral by a pair of angular brackets. So if I do that, the radiative transport equation looks like this. Oops. So you have theta dot grad u, that's the directional derivative in direction theta, is given by sigma times the average minus sigma times u. So that's my simple model for light propagation. And so I claim that this is a relatively good model for light propagation in a moderately scattering regime. And I have a picture here that I took. This is from ancient times, back when we were allowed to fly airplanes around the country willy-nilly. This is actually a photograph that I took the last time I flew out of Kentucky on an airplane. And so what's going on in the photo is it's a photograph that I took out of the window of an airplane on a hazy day. And so the haze, the little particles of, I don't know what haze is made of, but the little haze particles in the atmosphere are scattering, right? So light is bouncing off them and doing strange things. So in the foreground, right? Let me see if I can zoom in on this picture without disturbing my talk too much. So in the foreground of the picture, you see that there's not very many haze particles between the ground and the camera, right? So light is basically traveling as though it were just traveling with simple transport. So the directional derivative is 0 up in this equation here. But as you look sort of into the middle ground, so there's a longer distance between the camera now and the objects over here. And so there's more haze particles in the way. So the light isn't just reaching us by simple transport. Some of the light particles that are starting here have been scattered out of our field of view. And we're also seeing, when we look in this direction, some light that comes from other particles from other places that's been scattered into our field of view here. So we begin to come into the regime where the radiative transport equation models light propagation better than the ordinary transport equation. And as you go into the far field, you see, like, as you put more and more air between the objects that we're looking at and the camera, there's more and more haze particles. So you're getting into a regime where the RTE sort of has more and more force, right? So that's the scattering term has more and more size, relatively speaking. So this is a little bit odd because really what's happening here is that there's greater distance involved. So there's more particles to be scattered, but you can think of it as like sigma is increasing, right? This is sort of equivalent if you think of this as a scaling argument. So the RT is playing a more and more larger and larger role. And you think of the RT as basically modeling light propagation in this kind of a scattering argument, in this sort of scattering regime. Okay, let me go back to my regular slide size if I can. Okay. And okay, so one more thing though, if you look in the really far field, right, of this picture, sorry, I don't mean that in a technical sense. I just mean if you look in the background of this picture far away, everything is really blurred out, right? In the far near the horizon here, it's not just a question of distance. Everything is just blurred out entirely in terms of the detail. And that's because, if you like, there's so many haze particles between you and the points near the horizon that you can think of light not so much as just following the RT, but really doing a kind of random walk between here and there, right? There's so many haze particles that the sort of straight line transported light is not really dominant. And what's really dominant is light particles that have bounced around a lot and sort of done a sort of random walk. So you can think of, in addition to the RTE, which serves as the transport model that I was talking about earlier, in addition to the RTE, you can also think about diffusion models. So if you think about what's going on in this, in the part of this picture up here, if scattering is so dominant that photon trajectories can be thought of essentially as random walks, we can extend to use a diffusion model, where you say the light intensity U satisfies a diffusion equation. And if you're wondering why there's no time dependence in the diffusion equation, right, the point is that light comes to a steady state very quickly. Light is famous for moving very fast. And so we're just, that the time dependence drops out, and you're just left with this elliptic equation satisfied by the light intensity. So you think of light as doing this sort of weighted random walk weighted by sigma, and then you say that it satisfies this elliptic equation here. And so this gives you a model for light propagation in a regime where scattering is really dominant. So you can think about the back of the picture. Okay, so those are my two models. And then the only other thing that I want to say here is that, I've talked about how, like, as you move from the front of this picture to the back, you're sort of moving from a regime of transport to a regime of diffusion. And you can actually make sense of that in some sort of meaningful way. So if you think about the radiative transport equation with this scaling factor Kn inserted here, you can think about what happens as Kn goes to 0. So this scattering term becomes very, very large. And it turns out if you send kn to 0 in this equation, the solutions to the RTE can be understood as approaching solutions to this elliptic equation. Right? That's the same sigma in both cases. You can think of the solutions to this equation as approaching the solutions to this equation in a certain sense. So I won't say too much necessarily about how or why that is, but I think this is an important point of view to keep in mind. Okay, so these are my models, and let me just remind you that in the outline, what I want to talk about is I want to talk about what tomography problems look like with local data look like in these two models, and what inverse source problems look like in these two models. And so, by the way, right, so by local data, I mean that we're restricted to making boundary measurements only on a certain subset of the boundary. So we're not allowed to gather boundary data from all around our domain of interest. We're restricted to considering boundary data only on a fixed subset of the boundary. So this is a problem that has a lot of practical implications, right? Because in practice, it may be impossible or impractical to gather data from all around the boundary. So this is a very interesting problem. I want to point out that the 4 problems that I'm talking about here are all solved in the full data case. So as we'll see, if you think about optical tomography with a diffusion model, essentially you have a sort of cauldron type problem, which for full data was solved, I guess, by Sylvester and Ullman in the 80s, also by Nachman in the 2-dimensional case. And there's many other papers on this problem. The transport tomography model is also solved in the case of full data, known to me by the papers by Shui and Stefanov, but there's also papers from other authors in this area as well. For the inverse source problems, I think attribution for the diffusion models is a little bit complicated depending on what version of the inverse source problem you're considering, but suffice to say that these have been settled for a long time. And then for the transport model, there's these papers by Stefanov and Ullman, and also Ball and Thomason that deal with inverse source problems in full data. So these are problems that are well understood for full data, but as we'll see for local data, there's a variety of statuses of these problems here. So I want to start by talking about optical tomography with the diffusion model and say a little bit about what that looks like. So let's see. So I want to consider the following problem, right? So you consider the problem where U satisfies this sort of elliptic equation inside omega with a given boundary condition F. And the question is, if we set E on the boundary, can you determine sigma from measurements there? So let me draw a picture so you all have something to stare at for a second. Oops, what have I done here? Just need the zoom thing on the top to go away so I can actually access the draw capabilities. No, okay. This is not what I want. Okay, let's try this. That was more complicated than I wanted it to be. Okay, so let's see. So let me draw a picture so we all have something to stare at. This is something I won't try again, hopefully. So you have some domain omega, right? And inside omega, U is satisfying this elliptic equation, and it's given some boundary condition F. And so what I'm saying is I'm going to fix a part of the boundary E, and I'm allowed to measure U and its normal derivative on E. So I'm allowed to measure U basically as much as I want on E. But to fix a solution to this equation, I need to tell you something about what U is doing on the rest of the boundary over here. And so the thing that I've said sort of arbitrarily is that I've set F, which is the boundary value of U, to be 0 on the part of the boundary that's not E, right? So all over here, you have U equals 0. So optically, maybe this is a bit of a strange boundary condition to think about. So you've just declared that the light intensity field is canceled out on the back. So you can imagine you've like wrapped your object in black velvet or something like this, which is maybe a bit of an unnatural thing to do. But the point is you need to set some boundary condition in order to fix U on your domain. And this is sort of the mathematically natural and easy thing to think about. So I've just set U to be 0 on this back boundary. And so I've asked basically if you can measure U in the normal derivative on E for all solutions basically that vanish on the back, does this determine sigma? And the answer to this problem, oops. No, I just keep not sharing the screen. Okay, hang on, I'll stop doing this. Hopefully I'm not leaving you too much in suspense about what the answer to the problem is. So the answer to this problem is nobody really knows in the general case. So there's a number of results. Oh man, I meant to draw something else here, but now let's see how easy this is to do. Okay. So there's a number of partial results in this area, and I want to mention in particular this result by Gonzalo that says that if you have a domain where the set where you're not measuring coincides with some sort of geometric object, then you're allowed to recover sigma from the measurements on E. Right, so if you have a set like this, where the unknown, the set where you're not measuring, the set of ignorance, coincides with a hyperplane or a hypersphere or a hypercylinder or some other from this collection of geometric objects, then you're allowed to reconstruct sigma from E. Okay. But there's sort of this geometric restriction on the sets that you're not measuring on. And the reason for that is basically that these results rely on the construction of complex geometric optic solutions. And it turns out there's a bunch of geometric restrictions on how these objects can be created. And that sort of translates into the sort of sets where these solutions are allowed to vanish. And that translates into this restriction on the sets where you're allowed to not measure. And there's a number of other results in this area. I just want to mention a couple. So this paper by Gonzalo relies on this sort of Karlman estimate approach. There's also this paper by Viktor Isakov, which relies on a reflection argument and has some sort of similar results. And there's also some results for similar equations that are not quite the same. So there's this paper by Dos Santos Ferreira, Koenig, Schoenstein, and Ullmann that deals with the linearized version of this problem. And then that sort of technique is also used in these papers by Kripchuk and Ullmann, Lassos, Limatine, and Zelina and Salo, to talk about also what happens when you have nonlinear equations, so nonlinear versions of this problem. But as far as the general local data version of this problem is concerned, this is still, as far as I know, an open problem. Okay, so you have to live with these geometric restrictions, or conclude that it's an open problem. Oops. Sorry, I keep accidentally not sharing the screen, but maybe the solution is I will try to stop drawing as much as I can. Okay. So that's the status of the diffusion of the tomography problem in the diffusion model. And now let's think about a little bit about what it looks like in the transport case. So to state the local inverse problem in the transport case, we need to begin by understanding the boundary conditions for the RTE. So you define these things called the incoming and outcoming boundaries, d omega minus and d omega plus, by basically saying d omega, let's think about d omega plus here, since it's the one pictured. D omega plus is the set of pairs x theta, where x lies on the boundary and theta is a direction. It's a set of pairs x theta where x lies on the boundary, and theta dot the normal vector is greater than 0. Right? So roughly speaking, theta points in the same direction as the normal vector. So you imagine you have a point on the boundary. The directions theta that point out of the object, as pictured, are the ones in d omega plus. I guess that should be a d omega instead of gamma. So it's representing basically the set of points on the boundary combined with the outgoing directions theta. That gives you the terminology outcoming boundary. Okay. And then the incoming boundary is just the opposite, right? So it's the set of points on the boundary and directions where the direction points inwards. It points in the opposite direction as the outgoing normal vector. So the set of x theta where x is on the boundary and theta points inwards is called the incoming boundary. And the natural boundary condition for the RT is to set u on the incoming boundary. Right? It's to say what the incoming light into the domain is. So with that in mind, the basic inverse problem is as follows. So you have the RT within omega, and you're saying I'm going to set u on the incoming boundary to be f. And then if we pick a domain E inside, or if you pick a subset E of the boundary, and you say I can measure u on the incoming and outgoing parts of that subset of the boundary for data where you have no incoming light on the rest of the boundary, does that determine sigma? Right? So I'm not going to try to draw again, lest I stop sharing again. This is the same picture as before, right? So you've picked a subset of the boundary and you're saying, I'm only going to measure on that part of the boundary. I'm only going to restrict to data on that part of the boundary. And I've set u on the incoming part of the rest of the boundary to be 0. And I want to know if I can determine sigma using that data. Okay. And it turns out that under reasonable conditions on E and omega, the answer is yes. So in particular, if omega is strictly convex, and E is any open subset of the boundary, it turns out that you can do this. You can determine sigma from this Cauchy data set. And so this is explained in recent work of mine. And so I want to take a few minutes to talk a little bit about how the proof of this works. Okay. So the idea is based on something called the collision expansion for the RTE. So the way this works is that I can take the RT and I can write it out with the integral term on one side and everything else on the other. And I can say that, okay, so the stuff on the left, I'm going to label T. This is basically just a transport equation that we can solve as though it were an ODE. And the stuff on the right, I'm going to label K, right? So this is the operator K applied to U. And I can say like T, I understand very well, right? T is a transport equation. I know how to solve a transport equation. So there's a right inverse, T inverse, that I obtain to the operator on the left side by solving the transport equation. So I can basically apply T inverse to both sides of this equation, right? So when I apply T inverse to K, I get T inverse of K. When I apply T inverse on the left side of T, I get U up to something in the kernel of T. So if I apply T inverse to both sides of the equation, what I find is that I have U minus T inverse of KU is equal to something in the kernel of T, which is to say that something that satisfies the transport equation theta dot grad U plus sigma U equals 0. And I can pick the boundary condition of that thing in the kernel to give me the right boundary condition. So by taking the inverse of the transport equation and applying it to both sides of the equation, I get something that looks like this. So U minus T inverse KU equals this thing that solves the transport equation with the right boundary conditions. And then it turns out that T inverse of K has operator norm strictly less than 1 over any LP space, at least if your domain is bounded. So you can take this equation here and you can write out the solution U in terms of a Neumann series, right? You can just write out it's 1 plus T inverse K plus T inverse K squared plus T inverse K cubed, all applied to JF. And this expansion is called the collision expansion for U. And the reason why is because if you look at the terms, they basically talk about the light that's, so the nth term talks about the light that's collided with something and scattered n minus 1 times, right? So the very first term in the collision expansion, JF, corresponds to light that just satisfies a transport equation, so it moves in a straight line without any scattering. If you look at the second term, T inverse KJF, right? So JF is the light that moves in a straight line. K of JF is an integration of this up in angles. And then if you look at T inverse, you're saying this is satisfying the transport equation again. So you're looking at light that's evolved according to a transport equation, right? That's JF. And then you've integrated it up in angles and you're spitting it out in some new direction according to the transport equation. So this is light that's scattered once. It's traveled in a straight line, it's scattered once, and it's traveled out in some other direction. And you can interpret the terms of the collision expansion in this way, right? So this is light that's scattered 2 times and 3 times and so forth. And so that's the name, the collision expansion. And the beauty of this collision expansion is that because this T inverse and K are integrating operators, the terms of the collision expansion are progressively more smooth. So, right, so K is this integrating operator, it's integrating up in angles. So it's this sort of smoothing operator. And T inverse is also an integrating operator, right? You're solving a transport equation, so you're integrating in space along some line. Okay. So this T inverse K makes the terms of the collision expansion less smooth. And if you think about a very singular source, you can actually see this in a picture, right? So if this is a picture notionally of laser beams shot through some sort of scattering medium, which I took, by the way, from a presentation by Plum and Stefanov to illustrate the same concept. So what's going on here is that you have a laser pointer, right, which is a very singular source. It's a source that's a point source both in position and in angle. It's just firing through at a particular angle. And what JF here is this source traveling just without scattering, right? So how do you see JF? You have to be on this line, looking in the right direction, and then you'll see a very, very bright source, right? It's only supported on this very, very small set. When you apply T inverse K to it, right? So you're integrating up along angles, JF, over all of this set. And then you're spitting it out according to the transport equation again, right? You're applying T inverse to this term. So this second term, if you think about it as corresponding to the light that's scattered only once, it corresponds to light that reaches you by traveling down this beam, scattering once, and then coming out to your eye. So this is also somewhat singular, right? You can only see this light if you happen to be looking in the exact directions of the beam. You can't see this light in all directions. It's not supported everywhere. By the time you get to light that's scattered twice, that really is supported everywhere if you have a scattering medium, right? So everywhere you look, you'll see light that has come down from one of these beams, scattered once into some point of this medium, and then scattered to your eye. You'll see that at every point. That's this cloud of light that you see throughout this whole scattering medium. So the scattering, the collision expansion is really nice because the terms of these are progressively more smooth. And so in particular, if you have a singular source, you can sort of pick out these first two terms by their degree of singularity. And in the full data problem, this is exactly how you solve the tomography problem. Right? So in the full data problem, what you do is you pick a sufficiently singular boundary source. You isolate the ballistic term of the collision expansion by its degree of singularity. And then you say the ballistic term just satisfies the transport equation, theta dot grad JF plus sigma JF equals 0 with no scattering. So it just represents light that's traveled in a straight line with some absorption, but no scattering. And you can use this to solve the full data problem fairly easily once you've isolated this term. Because you're just looking at light that's traveling in straight lines with some attenuation. If you measure the difference in light between where you started and where you ended, you basically end up with the integral of sigma through this line. And if you know the integral of sigma through all these lines, you can just recover a sigma by inverting the X-ray transform. Okay. And so this is basically how this paper by Shui and Stefanov works. So you pick very singular boundary sources. You look at the collision expansion. You isolate the ballistic term of the collision expansion because it's much, much more singular than everything else. And then you use that term to solve the problem. So in the partial data case, in the local problem, if you restrict both sources and measurements to a fixed subset, I call it gamma here and E here, but I should just call it E. If you restrict both sources and measurements to some fixed subset E of the boundary, in general, you can't measure the ballistic terms on E. Right? So if you imagine starting with a source on E and firing your laser pointer off into the distance, in general, the ballistic term with no scattering will just never again return to E. You'll never see the light from that laser pointer again. So the full data approach in the local problem that's based on the ballistic term does not work. You can't expect to see the ballistic term in general if you're restricted to a subset. And so you have to basically, what you can do instead is you can recall that in a collision expansion of U, if you have sufficiently singular boundary sources, right, the ballistic term is particularly singular, but the first collision term, the single collision term, is also a little bit singular, right? It's not supported everywhere. You can only see this term if you happen to be looking in the exact direction of the laser pointer beam. So you can still separate out this single collision term from the rest of the collision expansion by its degree of singularity. And in general, it's not really clear what this term does for you because it's so nonlinear in terms of its dependence on the coefficient sigma. Right? So if you think about the light, if you think about shining a laser pointer from this point here, and then measuring what's scattered here, what you're seeing is the total attenuation between here and here. And then you're seeing that multiplied by sigma, and then that's further attenuated by what sigma is between here and here. So it's highly nonlinear dependence on sigma over this sort of weird broken ray. And in general, it's not clear what the first collision term can do for us. But if you're very particular about how you measure your first collision term, so in particular, if your point source and your measurement location coincide, then it turns out this term takes a really nice form. So let me try to explain this if I can. So if you think about shining a laser pointer from this point X in this direction and asking about what you see at Y, you basically see the light that you started with times this attenuation factor alpha, where alpha is like, e to the minus integral sigma. This comes from solving the transport equation. So you get this attenuation factor between X and Y. And then if you multiply that by sigma to represent the scattering, right? So now you're thinking about what KJF looks like. You have this alpha of XY, and you've multiplied it by this scattering function sigma. And now if you want to say, like, what's the result of all of this when I measure it back at X in the first place? I have to attenuate this alpha XY times sigma Y. I have to attenuate it again by the attenuation between Y and X. So that explains this term here, right? So what I'm seeing at X due to Y is I'm seeing the attenuation between X and Y multiplied by sigma of Y times the attenuation between Y and X. And if I imagine shining this laser pointer and looking at my actual measurement at X, what I see is the integral of this thing over all of the Y's that live in this line. Okay. And so I have this particularly neat form for T, for this first collision term. And you can see that this is like somehow like, this is this super nonlinearity thing that I was talking about. Alpha depends on sigma, this alpha depends on sigma, and sigma also, of course, depends on itself. So you have this sort of extreme nonlinearity in sigma represented in the first collision term. And so in general, you might still think to ask what you can recover from this, but it turns out that if you think about this, what's inside this integral just happens to turns out to be something really nice. And you can already almost see it if you stare at this hard enough, right? What's inside the integral looks a little bit like the derivative of this alpha of xy. So if you think about what happens if you take the derivative of this alpha of xy, you're just going to get alpha of xy back again times a sigma, right? So you're just going to get this thing. And this extra alpha of xy isn't going to interfere with you too much because the attenuation from here to here is the same as the attenuation from here to here, right? So you're really just putting a factor of 2 in front of this integral. And it turns out that the thing inside the integral is the derivative of a very nice quantity. So when you integrate it up, it turns out what you're really just doing is you're looking at the difference between this quantity at x and this quantity at the end x theta. So it turns out that the thing inside the integral has a really nice form, and what it gives you is the difference between the attenuation from a point to itself, which is just no attenuation, right? It's just the factor of 1, and the total attenuation between x and the opposite side of your domain. So it turns out that if you're very careful about how you pick your source and measurement, then this super nonlinear thing just happens to give you basically the integral of sigma over the line L. And so what happens is that you can recover the integral of sigma over all of the lines L that pass through your domain E. So you obtain the integral of sigma over all lines through E, and this gives you a local X-ray transform of sigma. And it turns out the problem can be solved if this local X-ray transform is invertible. And so in particular, the thing I said, if E is any open subset of the boundary of I should say strictly convex set, we can recover sigma from this transformation. And so there's this very nice solution to the local tomography problem with transport that says that if you have a convex body in any open subset of the boundary, then you can recover the optical coefficient sigma from measurements on E. Okay. So there's this really nice resolution to the transport problem, at least if things are convex. If things are non-convex, everything becomes much trickier, right? Because you're no longer allowed to consider the first term, the single collision term in the collision expansion, right? So in order to see this part of the domain, the hidden part of the domain from E, you have to consider light that somehow has bounced here, bounced into the hidden region, bounced back out, and then come to E. So you have to consider light that's collided with a scatterer at least 3 times. So non-convex domains are sort of really tricky, and I don't necessarily have anything very clever to say about this. But at least in the convex case, this is sort of really nice solution. Okay. And so you might ask yourself, okay, so if the diffusion problem can be thought of as a limit of the RTE one, does the solution of the local RTE problem shed any light on the local Calderon problem, on the local diffusion problem? And the answer is probably not, as it turns out. Right? So the problem is that if you send sigma to infinity, which is what you do when you scale sigma, right? Scale the Knudsen number Kn. You're sending this attenuation factor to 0, right? You're sending e to the minus integral sigma to 0. And what that means is that each individual term of the collision expansion tends to 0. So you can't meaningfully extract information from any particular term of the collision expansion. And there's this really nice quantitative analysis of this phenomenon in this paper by Lai, Li, and Ullman, where they analyze this for the full data problem. Right? So they take the full data tomography problem for the transport equation. They look at what happens in the limit as you scale Kn to 0. And you see that indeed the stability of the problem drops off as you would expect. And so the solution of the transport problem doesn't really say anything in particular about the diffusion problem. I guess while I'm here, I might as well also make a shameless plug for my own paper with Ruyu Lai and Chin Li that analyzes a hybrid problem, the same phenomenon in a hybrid inverse problem for optical tomography. But basically the problem is that you're solving the RTE problem by relying on these very singular terms in the collision expansion, and these sort of go away in the limit. So it's possible that there is a way of solving the local RTE problem that carries over to the diffusion problem, but sadly the thing that I've described is not it. Okay. But so this situation where the transport problem is solvable and this diffusion problem is very difficult to solve is actually sort of reversed in the case of inverse source. And so I wanted to spend the last few minutes of my talk talking a little bit about that. So what is the broader context of this thing? So I want to consider the following inverse source problem for the diffusion equation. So I'm going to here fix two subsets of the boundary E and F. And I want to consider what happens if I have a source at F and I'm measuring at E. So let me maybe risk drawing again. Let's try this. Okay, so I'm going to have a domain U or omega, and I'm going to fix a set F over here, where I've set a source. And I'm going to measure what happens to U over here at E. So what's the point of setting this up like this? Well, in part with this sort of boundary source. So in part, I mean, this is sort of natural when you think about optics, right? Normally when you think about seeing something, you're thinking about seeing a two-dimensional image. You're talking about like this sort of boundary recovery problem. So you're basically saying, you know, can I recover an image through a scattering medium? And the other thing is that if you consider like a sort of maybe more mathematically natural volume source problem where the source, you know, sort of lives on the interior, it turns out that this problem is ill-posed. And I think that's known as far back as Newton. So that's very well understood. So I want to consider this boundary source problem. Let's see, let me make my drawing go away. It turns out this problem, as I've stated it, is relatively easy to solve. And the reason why is that if you have two solutions that correspond to different sources that match to first order on E, you can look at their difference W and extend it across E by 0. So let me try to draw again. Right, so so I have this situation again where I have, you know, two solutions which in principle might differ on F, but they're the same to first order on E. So if I look at their difference, I can extend it across E by 0, right? So I can imagine extending my domain a little bit and defining U minus V to be 0 here. And because they match on first order to E, what I get is a solution to the original diffusion equation on this extended domain, which vanishes in an open subset. And then there's a standard unique continuation result, which I guess is due to Carleman, that says that U has to be equal to V on the entire domain omega. And so in particular, they had to be given by the same boundary source back on F. And so the nice thing about this result is it's true no matter how crazily non-convex this domain omega is, right? So if you have some sort of like domain with a bunch of corners here, this result still holds, right? So if you have F over here and E over here, it's still true that the measurement at E determines what's happening at F. It turns out for the inverse source version, for the transport version of the inverse source problem, things are not necessarily so easy, right? So you can ask a very similar question in the transport case. So you're going to pick an E and F inside the boundary, and you're going to set what F is on the incoming part of F, and you're going to measure U on the outcoming part of E and ask if you can recover the source S. Okay. And in the convex case where you can see F from E, it turns out that this is known. So hang on, let me try drawing again. So if you have some sort of convex set so that you can see every part of F from every part of E, then you can recover the source. So the paper by Mark Hubenthal is actually in terms of an interior source, but you can apply it to the boundary source problem as well. So that for convex domains, this is known, but if you have a non-convex domain, like the one I drew earlier, right, where F is over here and E is not here, F is not visible from E, things turn out to be much harder. So I also want to point out that Alexandra Thomason gave a nice talk in the seminar a little bit earlier, which talks about this sort of inverse source problem with partial data in 2 dimensions, which is, I guess, joint work between him and Fujiwara and Sadiq. But the point is, there's something you can say about this problem for convex domains, or domains where you have this sort of nice convexity problems, nice convexity properties. But for non-convex domains, things are sort of somehow much more difficult. Let's see, is there something more I wanted to say about this? Yeah, so the idea of the paper by Hubenthal is basically like it goes back to this work by Stefanov and Ullman and Bell and Thomason for the full data problem. Right? And basically what you're doing is you're doing something very similar to what Shui and Stefanov did, at least in spirit, right? You're saying that basically the RT is the transport, the ballistic term, plus some sort of perturbation, and you're going to deal with that perturbation somehow. So if you can see all of F from all of E, and you say, okay, it's basically the ballistic term plus some perturbation, then you can recover the source on F from the ballistic part. If you have a situation like this where you can't see F from E, right, the ballistic part is no help to you. And so this sort of accounts for the difficulty in the non-convex case. So I maybe drawn a little bit of a more professional looking picture here. So for non-convex domains, the problem is quite difficult, precisely because the ballistic part of the solution from F is not visible from E. And so you have this kind of strange situation where for the tomography problem, the transport problem can be solved, but the diffusion problem is difficult. And in the inverse source problem, it's the other way around, where sort of the diffusion problem is solved and the transport problem is more difficult. And so you could also ask, right, so is it true, because the diffusion problem can be thought of a limit as the RT one, does the solution of the diffusion problem shed any light on the local transport problem? And the answer is maybe, but you have to be a little bit careful, because it turns out that the unique continuation property that you're relying on in the diffusion equation does not hold for the transport equation. And this is a result, as far as I know, due to Guillaume Ball. And basically the reason for this is that you can think about like what happens if you have a source on F that's sort of pointed in this direction. So you send light in this direction. Right? So what do you see down here? Well, in a scattering domain, you're going to see this light that travels down here and then scatters to this point here. But you can also imagine canceling out this scattered light by, like, picking some negative light sources up here that do exactly the right thing to cancel out this scattered light down here. And so you can set up this situation where, at this boundary, you have no, you have basically no input whatsoever. And so down here, the solution to the radiative transport equation is identically 0. And so you have a situation where unique continuation does not hold for the RT, because it's identically 0 down here, but it's not identically 0 up here. And so you have to be really careful about how you're going to try to apply solutions from the diffusion equation. And I think in general, it's not clear that this sort of precludes a solution to the inverse source problem for the transport equation. But it's not clear how you would go about applying the diffusion ideas directly. Okay, so let's see. So in conclusion, so I want to mention that I talked about 4 optical inverse problems with local data, right? So there's this diffusion tomography problem, right? The tomography problem in the diffusion model, which is mostly unresolved, right? So there's some partial results due to people like Koenig and Solo, but it's really not clear what happens when you don't have these geometrically restrictive conditions on the part of the boundary that you're not measuring. And you can contrast that to the tomography problem in the transport model, which is at least partially resolved, right? At least in the convex case, we know what's going on. And it's sort of interesting to compare these two models, because you can also think about what's happening in the source problem, where the diffusion problem is mostly resolved, right? It's this sort of very simple problem that deals with unit continuation. And the transport source problem is sort of less resolved, right? It's only resolved in the convex case, and it's not really clear what's going on in the non-convex case. And so I think there's a lot of problems of potential interest that lie in these areas. Sort of there's some interesting problems in each of these unresolved places, right? So like, what is the resolution of the local cauldron problem, for instance? What is the resolution of the transport problems on non-convex domains? But then there's also some problems of like what's going on with the relationships between these 4 problems. So I kind of wanted to advertise this a little bit and say that there's a lot of problems of potential interest that lie in these areas. Yeah, so that's the summary of my talk. So thank you very much for listening, and I'm happy to take questions.
Thank you very much, Francis, for the very nice talk. Thank you very much. Are there any questions or comments, please?
Hi, Francis. I have a question. So your model is something I call the critical regime, where you have the attenuation and the absorption the same. Yes. And then the scattering kernel is identically 1. Does the results extend so your local results for the source for an arbitrary scattering kernel? So you have sigma of x, so it's inhomogeneous, but independent of the angle of scattering, and you also have it equal to the absorption coefficient. Yeah. And you are looking at the local problem, yes.
Mm-hmm. So in the most general possible case of the RT, if you're saying that all the coefficients of the RT are unknown, there's too much data to resolve, I think, just with the local problem. So certainly the thing that I talked about does not apply. If you fix a lot of these things, extra things to be known, like if you fix the form of the scattering kernel to be a particular thing, like a particular known thing, then you can do something very similar here. But I think in general, there's too much information to be resolved just from the local problem.
Thank you.
Hopefully answers your question.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Please feel free to unmute yourself. Okay, if not, thank you very much, Francis, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.